All right, hey y'all. So we're going over section 7.8 now, which is more about conservation laws. So it goes over conservation of momentum and conservation of energy. We should go and take a look at that. All right, let's go. Okay, so the first thing is that, here, let me pull up to the top. All right, so this chapter, like I said, goes over conservation of momentum and energy. And we're going to look at conservation of momentum first. And the first thing it does is that we're going to be looking at the system that I have drawn out there. So what we're basically doing is we're going to prove that it works. So one of the most prominent features of an isolated system is that it's translationally invariant. So that's just vocabulary from chapter or section 7.6. And that is if we transport all n particles bodily through the same displacement, nothing physical change. If we move everything exactly the same, it's as though nothing moved, is what that says. So we're going to go on that premises. If I picked up the whole world and I put it somewhere else, nobody on the world would know they moved. Assuming I moved everything else too. So yeah, basically we're going to take these three particles that we're calling R1, R2, R3, and we're going to move them with that arrow of epsilon. All right. So when we do this, this is what happens to their potential energy. That's what we're going to look at first. So the potential energy goes like this. So it's, since the potential energy is a function of where they are in space, placement, I guess, we end up with something that looks like this. Now we're going to assume that we have like infinite, even though I only drew three because I am not going to draw infinite R's. Yeah, so that's what happens. And since our potential energy is relative to where you are, if I just like, it's relative to where each thing is in the system with each other. So if we don't change how they move, it stays exactly the same as if we didn't add that epsilon to it. So it just looks like this without it. So that's cute, that's fun. Now the thing to know here is that it didn't change. So our delta potential energy is 0. Yeah, that's really it. And if our potential energy didn't change, then I can tell you our kinetic energy didn't change, which means our Lagrange thing didn't change. So really from just knowing that potential is relative to everything, it position-wise, and that I'm not altering where they are in relation to each other, I can tell you that nothing's gonna change. So yeah, we're starting with that premises still. So now we're gonna focus on that, like the difference of the Lagrange being 0. So I'm gonna highlight that. That way we all follow. All right, so let's start in on that. So if R delta Lagrange we know is 0, so equals 0. Thing we also know about it is that it would equal epsilon delta of the Lagrange delta of whatever that x coordinate would be for that R1 particle. So I'm going to call it x1. And that would be plus dot dot dot. And then it would go all the way out into the infinite dimensions. We're going to look at it as one-dimensional since all of our arrows pointed the exact same way. Which is really what you would do individually. Like the Lagrange is only looking at one dimension at a time. So we're chill. Great. And yeah. So basically what we see that coming out to is a sum, a gross, nasty sum. So that sum is going to state that the sum of, from alpha equals 1 to n, so the number of particles we have, is going to be equal to LE times this bad boy equals 0. We can drop the epsilon right now because honestly we could just divide everything by epsilon, and since it's 0 on one side, we don't care about epsilon one bit. That was kind of like a technicality to follow kind of the textbook's derivation of everything. Of like, gonna add something arbitrary to it, and then I'm gonna not care about my arbitrary function anymore. So that's very nice of it to do to us. And then what we want to note from there, what the textbook wants us to note from there, is a little bit about its momentum and what that says about it. So what that says is that this right here, so one factor in that sum is going to be, oh my goodness, it's going to be equal to the time derivative of that. So that's just Euler-Lagrange. Cute thing to know. And when we do that from chapter 7.6, we know that this term right here is just the momentum in that direction. So in other words, here's what it has us say now. Like that I've prepped and I didn't leave myself enough room. Wonderful. Okay. Here's what we can say about that from there. It is that, write this in green again, because we're going back to sigma notation here. The sum from alpha equals 1 all the way to that nth particle. Nth particle. We're going to replace what's inside the sum here with all this. So like individually, we're going to set it up for ourselves. So the time derivative of the Lagrange. That way we're seeing where we're getting it from, which is also sum alpha equals 1 to however many particles we have of that time derivative of our momentum. Okay. Which, after it's done being a sum, is literally just adding all the segments of momentum back into each other. So we can say that then that is total momentum, so that that whole thing right there just equals to our time derivative of the momentum in the x direction, and that's going to be equal to 0 still from our equation right there, which just means that our momentum doesn't change over time. It's conserved. Yeah, that's what we were looking for there. But it's just a little bit more explicitly stated. So now we're going to focus in on conservation of energy. And for that, we're going to like first take our definition of the Lagrange, but kind of the long one. It's not the one that's like nice for me to write. All right, so we're going to take that one, and that was a bad comma. That was a really bad comma, guys. All right, we're going to do chain rule from there. And when we do chain rule, the textbook kind of gives it to us in its form in sums, which I'm honestly gonna keep that. I don't want to do the work for it. But it does explicitly say it's like I'm using chain rule. So we are using chain rule. So what that really is doing is it's just breaking it apart. And we know that I, in this case, can be anything. So that's what's important to keep in mind. Yes? Yes, there we sort of did each derivative at a time. So that's what that Lagrange is still equal to. I should probably. There we go. That's what that's equal to once you do your chain rule. So we're going to write that out a bit nicer to see what it does, what that means for its momentum, which is basically kind of like this part right here. It's kind of just more of a reminder than actually contributing to our efforts. It will eventually, but like just kind of getting used to seeing this. Which is equal to all of our p, that I direction, and it's time derivative. Great, we nailed it. We got it. Okay. So from there, we're gonna use this information we have right here and fill it in for this and this, just to make everything a lot nicer on us. And that'll contribute a lot more to our energy in the long run. So we get that if we were to take the time derivative of the Lagrange, I'd definitely put the T on the wrong part of that. There we go. It's better now. Okay. It would be what we saw up there. So I guess this is like, this is dt. I knew I was missing something. I was like, why would chain rule give it exactly the same? Bam. Okay. Sorry, my computer was fighting me there for a second. But it's all better now. Okay. So what it does is when we plug in the red that we had into our initial black or our second black equation, we end up getting this right here. Yeah. So that's what we get. And then we're going to take it just a little bit further. Yeah, because if we notice that there's like a lot of dots going on here, because there's a dot there, dot there, dot there, we can pull out, this is so weird, but we're going to pull out a time derivative. And what we end up getting from that, as the textbook has claimed to me, and I have accepted, is just going to be this right here. So basically the momentum in the direction times the direction it's going, the sum of all that, plus the time derivative of the Lagrange, in which this part kind of irritates me because this is the same as this, but they're like, the time derivative is going to be the time derivative plus the time derivative. And honestly, I'm not going to lie to you, it's really annoying to me, but we're going to accept it because it worked out for them in the end. So what's then going to happen is So if we move the left side of this equation, so I'm not highlighted in green, this left side right here, we move that bad boy over to the right side, then we see that it's equal to this, and they'll cancel, and we'll be left with something much prettier, which is just going to be this right here. Here, I'm going to write it out nicer. But what the textbook then is like, if you subtract something by itself, you end up with this. And then it kind of like, it like was like, and then we put the time derivative back in. So the book did a few weird things just in a paragraph without telling us about them. So we're just gonna kind of like take it, I guess. Great. Minus L equals 0. And it's like, we're gonna keep the L, even though things should zero out a lot better. So we're just gonna keep the L. I'm gonna be honest with you, the textbook was not amazing at explaining this section, at least to my satisfaction. It was like, we subtract itself by itself and we get something different, but kind of the same. And I was like, I don't know if that's how subtraction works, bud. But he went out there for it. So I accept it. I accepted it. Just because I'm trying to learn from the textbook. All right. So then it's like, I'm going to bring up this totally new thing. So here we go. It wants us now to know the Hamilton of a system, which we've kind of used before. This is a different Hamilton of a system. So that is fancy H. And it's going to be equal to the sum I equals 1 to some number n that PQI dot, oh, sorry, they had factored the time derivative back in to make my life weirder. So this top equation is actually time derivative of the coordinate. Yeah, they really did it to me. I'm not gonna lie. Oh. So that minus the Lagrange. So basically, it's sort of taking this and it's like, it's my principle now. So that's what the Hamilton of system is. It's kind of a weird way of taking the derivative of the Lagrange without actually ever taking it. So what's really important is this part. It's not so much how we get there, it's that we got there eventually. So that Hamilton is really what we're going to end up using as far as knowledge in the class. And then it wants us to note a few important things about the Hamilton. So I will. Here it is. Here's your important thing. It's just total energy. That's right. Because what that is really saying is that the Hamilton is equal to T plus U. And why we care about that at all is that we know that the Lagrange is equal to T minus U. So this is like the actual important part of the entire chapter. The rest was just like, I'm going to teach you stuff that I know. And I was like, thanks. What do I need to know? And it was like the end of the chapter only. So here we are at the end of the chapter only. So from there, what it wants you to kind of note is it got there. Okay, I want to show you how we got Hamilton to be the total energy. And that is going to do with this right here. So that's my little note. Here's my proof that Hamilton is total energy. Okay, so I know that kinetic energy is 1/2 the sum of all the masses plus all of their velocities squared. I know that. And I know that the velocities of these guys are going to be the sum. You ready? Of their, oh my goodness, velocities over some coordinate system which is really just saying my velocity is going to be how my coordinates move with time. How things work with time is how my velocity is going to work, which is lovely to know. Which then means that this r dot alpha squared that we see right here is going to be equal. Okay, so this is how the book breaks it up. It's going to do two different systems, a J system and a K system. And it's just sort of different notation. It's saying the same thing as before. It's just like, this is how to write it down better. Oh, wow. Oh my goodness. That was quite the struggle my computer decided to randomly put up. Okay. Times sum. It's time in K. It'll be the exact same thing. It's time with K though. There we go. So that's a bit more of what we use during like the derivation part of it, just so you know where that got pulled out from. So now what we're going to do is we're going to look a little bit more at what that means for the total energy. Or not the total, the kinetic energy. This is T. Got thrown off by the T. Okay, so rewriting T, knowing all that, we're going to get 1/2 of an epsilon. This is the new notation. So it means this. And we're writing it in a new form. So this A is going to be whatever that sum actually is. But like there will be a coefficient that allows us to just end up multiplying them. That way we can see it better. That's not a G, that's supposed to be a Q. Yeah, didn't need that. Okay. There we go. So that's what that brings down for us. And then just a more explicit side note of what AJK is, or yeah, JK is it's actually like a function. This is how the textbook defines it. And it is what it's them pulling from kind of like different things from this equation up here. Yeah, okay. So that's just more explicitly showing you what it is. It's some functional thing that just allows us to write it nicer. There's honestly, this chapter is a little bit of me putting a lot of faith in the textbook. I'm going to be super freaking honest with you, but we'll get to the end and I'll tell you the important things, which is really just that Hamilton. So the momentum which is going to be, okay, if I do this, and I take the derivative, take the derivative, it's like q dot I end up, there's so much going on here. Okay, I end up with this. I'm taking the derivative of Lagrange with respect to that, okay? And I know this is where that t actually comes in. So this is like things I already know. This is where we're actually putting that. And that's the relation we end up seeing, which we're going to write out as exactly what we have there. Okay. So that's what we are doing with that, and think, yeah, so I can be anything in this. So when we did I, the textbook, without telling me, was like, an I is going to be K. So that's one of those tricky throws that the textbook just sort of does, is like one of the two coordinates will drop, and you'll end up with this last equation here that I highlight. Yeah. Okay. So now going back to the idea of like summing it all up, that q dot this, it's not q, it's supposed to be p. I don't know what I did, but I did do something. So the sum of p, I still don't know the difference between p's and q's, I guess. Some of this bad boy, p qi dot, is going to be equal to the sum. Here's me splitting apart that notation I worked so hard for. Not really. I just really trusted the textbook there. I remember learning vaguely about the notation in class, and I was like, this seems right. Which is also going to be equal to this notation. So I guess this part right here was kinder, and it broke down the notation more. And it says that's going to be equal to 2t, which I'm going to show you right up here. This is 2 of this, because it doesn't have a 1/2 in front of it. That's what that was saying. That's what that was going on about. It's like, when you don't have a 1/2 in it, it's doubled. So that's literally, we did all that work to find that out so that we can now prove, get this bad boy up here, now prove that this equals this. Here's how I'm going to do it, because I'm going to scroll back up real quick to show you all how we're about to do this. We're going to use this equation right here. So this part is what we just solved for, way at the bottom, that equals to 2 times the kinetic energy, so 2t. And then this thing we kind of already know. So way back down here, there's our 2t that we solved for. Very well. Okay. So we know that it's going to be, this is sort of, I'm going to prove this. Great. So since this is the first term and it equals this, I'm just going to write this instead of the first term of the Hamilton. 2t. And then our Lagrange is going to be t minus u. I think you can all see where this is going, but we're going to carry it out. So 2t minus t plus u is equal to t plus u. End of proof. I've done it. And that is how this section works. So there's a lot of just like weird derivation techniques used that you don't fully have to understand to just know that this chapter is true. All you have to know is that Hamilton thing. So that's all for section 7.8. I'm going to add my notes in the comment section or the description section below.